Hey everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about stack versus heap in memory allocation. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for the latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, without any further delay, let's get started with the agenda for today's discussion. We will start this discussion by understanding how memory stack operates, following which we will deal with stack overflow error in programming. And finally, we will understand how memory heap operates. I hope I made myself clear with the agenda. Now, let's get started with our first topic, which is understanding how memory stack operates. But before diving directly into this memory allocation structure, let's first analyze how exactly a program utilizes memory in order to execute itself. Basically, when we write a program in our code editor, it pre-processes the complete code before even compilation. This pre-processing deals with the header files. It expands the macros and other constants declared with a hash sign. That means the libraries like standard input-output, string.h, conio.h that we include in our code at the beginning will get expanded for utilizing inbuilt C functions. Following that is the compilation. When you press the compile button in your code editor, the actual execution of your code begins. First, the compiler checks for the errors in your program, and with the help of a linker, it converts the written code into executable machine-level code. This machine-level code is in the form of binary numbers, that is 0 and 1. And as we know, machines only understand this language of 0 and 1. So once this executable machine-level code gets generated in a system, the code editor accesses the memory in order to store variables and perform operations. The beginning part of this .exe file or machine code file is responsible for allocating memory to the variables and functions included in the program. The process of loading all data entities into the memory is called loading, and the tool named loader in code editor is responsible for that. Well, now you must be thinking about what the code area in memory is. To answer this question, let me tell you guys that the memory compiler utilizes to implement the code is known as random access memory or RAM, which is further segmented into 3 different blocks. The first block of this memory segmentation or layout is called as code area. This code area stores the machine-level code generated by the IDE and performs the allocation commands inside it. If the variables, objects, or functions used in the program are static in nature, then they get stored in the stack memory area. Whereas if they are of dynamic nature, they get stored in the heap memory area. Having said that, let's first understand the static memory allocation using the stack memory area. The stack area primarily stores the global variables in the program, and after that it stores all the function calls and local variables. The local variables are the variables declared inside the function whose lifespan is equal to the time taken to execute a program. Additionally, the amount of memory set aside for this stack segment does not grow while the application is running. That means the operating system predefines the size of the stack, and it cannot be changed. To better understand this stack memory allocation using stack, let's take an example of a C program. In this simple C program, we have a function multiply that gives us the product of 2 numbers. And we have a main method in which we are just calling the multiply function to get the product of numbers x and y. So let us see what happens in the memory when this program executes. Primarily, there is no global variable in our code. Hence, the IDE will directly begin inserting methods and local variables into the stack memory area. All of us know that when the program starts executing, the main method gets invoked at first. Thus, in our program as well, the main method will get invoked first, and some amount of the memory from the stack will be allocated to it. Also, the local variables inside the main block will get some amount of memory according to their data type. The memory allocated to the main block inside the stack memory area is called the stack frame for method main. And the size for this stack frame is calculated when the program is compiling. Now, when the main calls multiply method, the stack frame for the function multiply gets created. And inside it, local variables n1 and n2 will remain until the function gets executed. Remember, when the control is at a statement, int_m is equal to multiply of x and y, the state of our stack memory area will look something like this. But once the control moves to the next statement, the multiply function will get popped out of the stack area. And similarly, when it reaches the end of the main block, the main function will also get popped out from the memory stack. When the main finishes, the program will also get terminated, and the console will return the output of your program. Next, we will talk about the stack overflow error in programming. When the program's execution starts, an operating system allocates some amount of reserved space to the stack structure. For example, let's say OS allocates 3 MB space of RAM to the stack memory region, and the program that is present on the screen is supposed to utilize this given space. The simple C program that we have taken here contains a method named func, which is a recursive function. The function that calls itself repeatedly until a certain condition gets fulfilled is called the recursive function. But if you observe this block of code, there is no stopping condition to halt this recursive function. Hence, once the execution of a program begins, this function will keep invoking itself. At first, the main function will enter the memory stack. After that, the function named fun will enter the stack memory area as the main function invokes it. However, once the function fun is invoked, there is no stopping condition to halt it from getting executed repeatedly. So the function fun will keep on adding in the stack until the stack memory is exhausted. When the memory allocation process occurring during runtime grows beyond the reserved memory for the stack, as we have seen in the previous slide, this is called stack overflow error. To understand this better, let's visit the code editor. For this particular code, we will be checking how the stack overflow error happens. So let's just compile this code. Okay, as you can see on your screens, our code has started with the execution, and function fun is calling itself again and again. So let's wait until our stack memory gets exhausted. As you can see on your screen right now, our program has failed because of a stack overflow error. This error is occurring due to an infinite recursion of the function fun. I hope you're clear with this stack overflow error now. So let's go back to our presentation now. Now let's understand the memory heap region in programming. We understood that we could not manipulate the scope of a variable which is getting stored in the stack. Or if we want to create a large array for which we are unable to specify size, then we cannot declare it in the case of stack memory. But when it comes to heap memory, both of these problems can be fixed. Unlike stack, the heap memory area is not fixed. Its size can vary during the runtime of a program. Additionally, there are no set of rules for the allocation and deallocation of memory. A programmer can totally control how much memory to use from the heap and till what time to keep the data in memory during the program's lifetime. And heap can grow as long as you do not run out of memory on the system itself. That is a dangerous thing also, and we need to be really careful about using heap for this reason. In the C programming language, we have functions named malloc, calloc, realloc, and free, allowing us to manipulate storage in the heap memory area. And the objects or variables that we are going to create using these functions are going to be of dynamic nature. So let's understand the process of dynamic memory allocation using a C program. In this C program, we have created a pointer z for which we are allocating dynamic memory using the malloc function. The malloc function asks for how much memory to give on the heap memory area in bytes. When we call malloc and pass an argument size of an integer, then we are commanding over IDE to provide us with 4 bytes of random memory. Once the size is allocated on the heap memory region, the malloc will return the void pointer to starting address of a created new block. In this case, it will be 200. When malloc returns this address to us, we will use typecasting to store an element at any given memory address. Additionally, if I want to remove this variable from memory address 200, I can call function free to deallocate the memory. In this case, when I add line free of z, the reference to address 200 will get destroyed and the data variable present at that address will get removed automatically. But again, I can use the malloc function to generate an address reference for the same pointer z such that it will point to a new memory address with the new value as well. In this case, the newly created void pointer provides us with the address value 48. And by using typecasting, we are storing value 9 at that pointed location. Moving ahead, let's also discuss about the heap overflow condition. The heap overflow is a hypothetical condition in which the operating system becomes unable to provide more memory to the heap memory layout. This is considered to be a hypothetical condition as these days computer systems come up with massive RAM storages. But there are 2 scenarios that still can cause a heap overflow error. The first one is when we continuously allocate memory without deallocating previously allocated memory space. In this case, RAM memory is ultimately getting used for heap storage. But it is unavailable for other processes. If this scenario happens in your program, then there are high chances of getting your RAM crashed, and eventually it will lead to a deadlock or freezing of other main OS programs. The second scenario is about explicit memory allocation to the massive number of variables. In this case, the RAM gets completely filled with heap area and the computer enters in a deadlock situation. On that note, let's visit the code editor and build up the programs for both these cases. We'll build codes for each of these scenarios here, but we won't run them since I don't want this session to stop because of a RAM or system crash. I would also prefer that you people should also learn the theory behind heap overflow rather than running it because it could cause problems in your computers or laptops as well. In the first case, we want to allocate huge memory to the heap area without using any deallocation operation. So to do that, I will use a for loop running till the huge number, and for each iteration, it will generate 4 bytes of memory on the heap. The lines of code that will allow us to do that are: for I is equal to 0 to I is equal to this enormous number, we will produce an iteration. And inside this iterative block, we will keep allocating memory to innumerable integer variables. And in the second case, we just want to allocate memory to the massive number of variables. So again, the code for this will be a one-liner where we will be passing the number of variables to the malloc argument field. The line of code that will allow us to do that is int *ptr is equal to int *malloc allocating integer variables using the size of function for huge range. Remember guys, it's not a good practice to implement these heap overflow scenarios in your systems, as you can clearly see the massive storage complexity associated with these lines of code. So refrain from executing them in your systems. Now let's go back to our presentation and contemplate all the key differences that we have understood till this time. The first takeaway from this discussion is stack memory stores only static variables, whereas heap memory stores dynamic variables. The next difference between stack memory and heap memory is that the stack overflow error happens when there is no halting condition for function invocation in a program. In contrast, the heap overflow occurs due to the allocation of enormous memory area to dynamic variables. However, these errors are almost impossible to happen as we do not directly allocate huge memory space to dynamic variables. Next up is the thread access for stack and heap memory allocations. The stack memory allocation is considered safer than heap memory allocation as the owner thread can only access the data stored inside the stack. Meanwhile, in the case of heap, it can be accessed by any thread in a system. The last key difference between stack and heap on our list is stack frame access is easier than heap frame access because the stack has a small memory region and is cache friendly. Still, heap frames are scattered throughout the memory, resulting in more cache misses. With this, we have come to the end of this video. I hope this video on stack versus heap in memory allocation was informative and exciting. If you have any queries regarding the topics that were covered in this video, then let us know about them in the comment section below and we will get back to you. Thank you so much for being here and do watch out for more videos from us. Until then, keep learning and stay tuned to Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.